as you may well know, TIBCO has been in a partnership with the Mercedes Formula One team. I think we're just entering our fourth year together. And we've done a lot of work, and there's a lot of data science and data involved, obviously, in Formula One. You know, they do masses of simulations, you know, something we often call digital twins, where you try and replicate a real life scenario or situation or process and convert that to a digital process where you can emulate it and start testing and predicting or analysing how to improve that sort of process and thing that you're working on. So while a lot of Formula One information and data is obviously heavily guarded secrets and how they make the car go so fast and the drivers do so well, one thing that TIBCO has done is we've built our own Formula One simulator. So this is an example of the simulator that we've run. We ran this at Big Data London last year. And here you can see we've got this Mercedes car and the game here. And let me just show you this running and give you an impression of what we actually do with this. So here we go. So here you can see the guy racing. This guy was very, very fast. And then, as we've been talking about, this is streaming the data live into a Spotfire dashboard. And if I just pause that, you can see it's got various stats coming out the games, which is the speed you're going at, where you are on your track, and all sorts of attributes, even implicated G-force that the driver's experiencing. So as people drive, it's instantly in real time displayed in our dashboards. But what we wanted to do was bring in data science. You know, what can we predict? And here you can see in the very top here, a little bit blurry in the video, but a predicted time. So we want to try and learn how we could optimize a driver's lap time and then learn about what makes somebody fast versus maybe a slower driver. So I want to just summarize some of the technology involved, because obviously when you go into data science, and certainly with something like Formula One, you combine a lot of technologies. So what we're actually doing in our simulator is using this, the Formula One official game. That's the same game that's used in official esports championships, and all the F1 teams enter that with their esports drivers, so it's become big business. And it streams the data live out, and we pick it up using a Flogo, which is an open source edge technology. And the real backbone of it is TIBCO streaming or Streambase, where it gathers all this data. It can do all sorts of things like running models in real time. So when Michael mentioned at the start, what we can do is have models that are predicting as data flows straight out into here. So every time we get information from the game, we can run a prediction. So we stream that all back into Spotfire, like you saw in that dashboard video. But what we're also doing is we're dumping all the data to Postgres, and that means we can use that data for historical analysis, for more in-depth modeling. And here, again, much like Stephen's demo of life expectancy, we've got the TIBCO data science part, building models, and what it's doing is it posts it out to our model repository, which then can update into our streaming application. And what's quite cool is when we did, so this is a real situation that we did run at Big Data London last year. We actually had models relearning and rebuilding as people raced, deploying in real time, and then going into the stream. So halfway through someone's lap, we flipped what model we were using to predict their lap time, and we could see in real time that that model had changed and better predictions happened as it learned. So just to summarize what I'm going to go into the details of the actual data science and the analytics we did, we set ourselves two challenges: predicting final lap time. So from the moment they're racing, can we predict? And that's quite hard early on the lap. You don't know a lot about the driver yet. But also, as we learned from watching people race our simulator, there's a lot of erratic driving, shall we say. So we thought it'd be quite interesting to see, could we predict the likelihood of someone having an accident where they damage their car? So before we start actually going into detail, I'll give you an impression of the data involved and just get an idea of how much data these games and esports games stream out. So we get all sorts of different information covering track and tires and heat and speed and things the driver's doing, how much they're braking. And actually just one lap of the Brazil circuit, which is what we're going to use in this demo, generates nearly 105,000 data points. So that's just one lap. And imagine you get a few hundred people trying the simulator for multiple laps. So it outputs 10 rows of data per second. of 130 columns, so it builds up very fast. So let me jump out into the actual demo. So again, much like the previous example, we're going to use Team Studio, our data science tool here, as the backbone where we collaborate. Here we can store things like PowerPoint, workbooks like we've seen before, Python notebooks, and also the Spotfire tools. So before we do the data science, what we wanted to do was learn how much can we learn from this data that we've got coming out of this game, how useful is it? So we built a Spotfire dashboard to do that. And this is what we've got. So I want to take you through examples here. So this is just one way we represented the data. So here you see the Brazil lap that we ran the simulator on at that event in London. And what we're seeing here is every single dot in this map, hopefully you can see it, is one data point that came out the game that was streamed out live. So the idea here is we want to analyze and learn from this. Could we learn to drive actually just from analytics without being in the car? So what we've done is we've colored the lap. So every point is colored. So I'll use this throughout this demonstration, but where you see pink or purple, that means they've gone very fast or it's the highest value. So in Formula One, when you say someone's going purple, it means they're doing the fastest time that anyone's done. So immediately we can learn by looking at the purple line, how to drive this corner. You know, you can see that the people who go very fast go this route, whereas the green and the blue are slow, and it's not such an optimal route. So you can learn about the best place to be in the track. So I want to expand on that example a little bit, because what we can do is highlight parts of the track and actually learn about very specific detail about what makes someone fast. So in this example, what we're going to look at is a corner, the approach into this corner. So Formula One tracks are split up into 3 sectors. The third sector, you know, is the last phase before you finish your lap. And what we're seeing here is we're going to look at the approach into this corner and then how people come out. This is really crucial to getting a good fast lap time at the Brazil circuit for Formula One drivers. So what we've done is we've highlighted the straight before the corner, and here we've got some statistics. The numbers here on the left are the lap times, so these are very fast drivers, that's 70-second lap time, 75 seconds, and on the right are slower drivers with 100 to 110 seconds. And we've got their speed and the percentage braking, you know, how much acceleration or throttle, how steep they're steering in, so what angle is they're steering at. And what we can see is we can learn from this very quickly. Even though we're on the straight, the people who finish up with very fast lap times here are going faster, as you might expect, but they're applying a lot of brake. So they're actually applying 75% or 65% of brake, so they're hitting the brakes hard, even though they're on a straight, not in the corner yet. Whereas the people who have slow laps around here are going slower, but they're not braking yet. And in fact, some of them are even accelerating. So if we move into the corner, we'll see how the behavior changes. So now we're in the corner, we're starting to get into the steepness of the left turn. And what you can see, interestingly, is the speed across all final lap times is quite similar. So what makes a difference? Well, actually, the people who are going fast aren't braking, so that's a little bit counterintuitive. They're not braking as much, even though they're turning a corner. And what you'll see is the people who are slow actually are braking as they come into the corner. Another thing to notice here is the angle of steering. So somebody who's going very fast, they've got a much steeper angle of steering. That means they're turning harder left than the other drivers. And that's a quite good insight to see, learn how to drive that better. So if we go to the final part of the corner, which is possibly the most important, when you come out the corner, you want to go really fast. And what can we see in analytics again? Here you can see that the people who are doing very fast lap times, they're almost full throttle. So that's high acceleration and pedal to the floor. Whereas again, people who are doing slower lap times, they're not got a lot of throttle. And what's interesting here is the steering angle is less, so it's straighter. That means you can point your car straight, which means you can go faster, and the slower laps again can't. So it's quite interesting, just from one analysis, we can learn how to drive without ever getting a car, just looking at the analytics. It's braking early, turning in tight, and it's getting on the acceleration early, straightening the wheel. But we want to do the data science around, so we want to predict how somebody's doing and what lap time they're going to do. So now we've done analysis and we've got a good understanding of the data, and I've used Spotfire mapping to this. We want to get into feature selection. So feature selection, where we generate features to build the model from, you know, we can't do this on the data that comes out the stream directly because it's too granular. So what we want to use is things like averages. So we've got a rolling 3-second average here, and we've got a cumulative sum. Again, purple points are where people are going fast. So if I highlight this as the fast drivers, and the slow drivers are sort of in a grey colour. And there's a lot of attributes. These are all the attributes that have come out of the game. We've got suspension data, we've got angles of suspension, steering, brake temperatures. There's a lot to go through. We could do this individually, but it's not very scientific, and we might not see all the relationships between it. So what we want to do is actually go back to Team Studio and get it to do the work for us using data science. So what I built was a track feature importance workflow, and it's a pretty simple workflow. So if I just open this and show you it quickly. So what this workflow is going to do is it's going to drag our data, so all our data from the Postgres database, so it's pulling from the same place that Spotfire did. We'll join it all together so we get the data in a nice one big table, and then we're going to generate our features, which is our 3-second averages that we talked about, rolling 3-second averages. But we're going to split the data into the 3 sectors that I mentioned of each track so that the models specialize in those sectors. And then we use an alpine forest, so a random forest, to actually build a quick model. Because one of the outputs of this random forest is actually variable importance, and we can see that table here. So we can easily build and learn what's the most important attributes in each sector. But again, we want to use Spotfire's visual power, so we can go into here and look at feature importance. And here you can see per sector. Interestingly, it's not the obvious things like speed, it's ERS, which is energy recovery system, engine temperature, X and Y, so the actual very detailed point on the track. So it's finding the relations that we might not have found as humans just by going through this manually. So now we've got some good idea of features we want to use, and we've got this workflow that we can call. And if I want to change my workflow and do a more in-depth analysis, I can do that all from Spotfire. So I can say use 100 laps, build trees that are 15 depth, and then just hit go, and it instantly reruns that workflow in Team Studio for me and outputs as you saw before. But we want to now use that knowledge and go back to our workspace and build some models to do our predictions. So if I go out to here, I'll show you the workflow we've built for this. So if I just open this workflow, and again, we did this in a collaboration. So I did some of the models, and then my teammate Nora, she actually built a Jupyter-based Keras model as well. So again, it's the same steps, joining all the data, using the same source, building our 3-second averages. But what we've done now is when we get to our sectors, we split into training and test, and we're going to build 3 different models. We've got a linear regression here, a gradient boosted regression, and we've also got this Python notebook, which we can open and again see how all that works. So write our Python code. So this is using Keras to do a neural network. So we've got a nice spread of different models, and we can then put out our predictions and export that for analysis. So when I run this through for all the training data, so we built a training data set for the event. What we can do is analyze which model predicts the best using a test set. So in Spotfire, again, we've taken out all the details so we can do some really in-depth analysis. And what you can see here is for each sector, you can see the R-squareds of each model. So we've got linear regression here, gradient boosting trees, and our neural network from the Python notebook. And here you can see they all struggle actually in sector 1, as you might expect. There's not a lot of information. It's early on the lap, and we get quite low R-squareds. Sector 2, all the models are about 0.6, 0.65. And then in sector 3, all the models get a lot better, as you'd expect, as we get more information to predict the final lap time. And you get some interesting trends where you can highlight and see what a model struggled with, but other models did well. We can also look at the residuals here as you go out throughout the lap, so the difference between the predicted time and the actual lap time, and see how much spread there is. So a residual average of 0 would mean it's pretty close to perfect. And here we can see the gradient boosted trees has got 1.3, which is a bit better than other models. So we took all this and we assessed it. Now we could mix and match models depending on the sector, but we've decided that gradient boosted trees is our best model overall, as you can see from the R-squareds. So one of the key parts was once we deployed this model, so we had to get this ready and we didn't have a lot of time. I think we actually built this in less than a week. We deployed it and had it running on the first day of the event that I showed you that video from. What we wanted to see then was how good or how much do the models learn. So we took those gradient boosted trees, and this is the same results from the first page where it's built on the data before we started the event. But we retrained the model in real time throughout the event and wanted to understand how much it was learning. So this is the same gradient boosted trees, but rebuilt with the first day after the event. So it's got about an extra 100 laps to learn from. And here you can see the R squared has improved a little bit for the first sector, quite a bit for the second sector, and then again for the third. And now our average residual is right on 0, so we're getting really close to having a nice spread. But there's some interesting trends here where you see big negatives at the start of the lap in certain models. So one of the key things is we can use R squareds and we can use simple things like root mean squared errors and other summary statistics. But really, if you want to understand, and we wanted to understand our model in a Formula 1 context, you have to put the data into the domain that you're looking at. So we wanted to look at all the models, but in a Formula 1 way. So what we did was we took some example laps and we plotted the predictions as the lap went through, as the person raced their lap. So this is the start of the lap here, end of lap, and this is all the predictions that happened throughout that. And here we've got the model in light blue before the event we trained it on, and then when it gets extra training data. So for instance, you can see the model here that was trained before the event really struggled with this lap, but then after the extra day of training, it was much more close to green line, which is the final lap time. But as I said, you might think that the models aren't very good when they've got big residuals. So for instance, here, the model's predicting almost 10 to 12 seconds less, so a much faster lap time than what actually happened. So it was predicting about 86 seconds when the person did a 96-second lap. If you took just the predictions from the first half of the lap, you'd think this model was really poor, and it would have a really low R squared with a big residual. But what we can see, and it's really interesting examples, when you put it in the context of driving, something happens here. So the red signifies a mistake by the driver. So here we can see the predictions at this point. And if I zoom in on the map, it shows us the points on the map where that person is. And it's all okay here, but they make a small mistake. So the models start to increase the lap time prediction before the mistake actually happened. So it looks like they touched maybe the grass here, but then there's a really big mistake that happens here. So there's a big spike because the models start to say you're going to drop lots of seconds. So again, if we look at that, here they're coming into this corner, which is quite tricky. And if we highlight this whole section, what you can see actually happened was the person came out here, overshot the corner, was going too fast, then spun, hit a wall, lost the wing, and then got back onto the track. So you can see the model's actually reacting to that. And these X marks are where they've damaged their car. So it does a big spike where it says, oh, you're in the wall, you might be doing a very slow lap now, and then it works out, well, you're back on track, you're going to do this lap time of around 96. But you see, even here, there's another mistake the models react to and predict before it happens, where the person overshoots because they've damaged their car and they've not got any downforce. So if you were assessing this model, you really should only assess it after the final mistake, because the predictions here may well have been very valid, but once the person makes a mistake, you cannot use the history to say whether this model predicted well or not. But here it is predicting very well before, after all the mistakes. So it's just very important to take that and put that into the context. But one of the really interesting things was the model's ability to predict accidents before they happened, which is not something we expected. So one thing we wanted to do was expand upon that a little bit more. And so just very quickly on our last slide, I'll show you what we then did with that. So we've shown that we can predict lap times pretty well. We've shown the models learn. We've learned about how to drive, but we also learned that people are pretty erratic, or people can be very fast and make a single mistake. So here we then decided to expand our crash predictions, where we started to model the likelihood in red of a severe crash, the likelihood in yellow of a minor crash, and actually try and model that through each lap as well. So we're running two predictions, not only predicting their final lap time, but based upon their driving and where they are on the track, how likely are they to damage their car?